In the unfathomable void of space, where galaxies drift like islands in an ocean of darkness, stars of unimaginable power come into being. Among them are the most enigmatic, magnetars. These rare stellar giants live fast, burning through their fuel at a rapid pace, their explosive death inevitable. Magnetars are more than just neutron stars. They are celestial objects unlike anything we can experience here on Earth, with magnetic fields that are trillions of times stronger than Earth's. Their energy is enough to twist the very fabric of space itself. But even the most powerful stars cannot shine forever. These cosmic beacons, magnificent yet deadly, eventually meet their end. And when they do, they don't simply fade away like the dying embers of a fire. Their death is as spectacular and violent as their existence, leaving behind a legacy that could shape the cosmos for billions of years. But what truly happens when a magnetar dies? Can anything survive the cataclysmic forces unleashed in its final moments? Magnetars are born from the explosive death of a massive star, one that has burned through its nuclear fuel and has no more energy left to fight the gravitational forces pulling it inward. When a star reaches this critical point, its core collapses under its own weight, triggering a cataclysmic event. This is the birth of a neutron star, a dense, incredibly compact remnant made almost entirely of neutrons. But for the most massive of these stars, the neutron star becomes something far rarer, a magnetar. Magnetars are neutron stars on steroids. They possess magnetic fields that are billions to trillions of times stronger than the Earth's, enough to rip apart atoms and disrupt the very structure of matter. This magnetic force is so strong that it can distort the pathways of light itself, bending the space around them. The magnetic fields give these stars an eerie power, one capable of unleashing devastating bursts of X-rays and gamma rays, far more intense than anything our sun could ever emit. But magnetars are not immortal. Their magnetic fields, which set them apart from regular neutron stars, are not a permanent feature. Over time, these fields begin to weaken. The rapid rotation of the magnetar also slows down, and its once dominant bursts of energy start to fade. But even as the magnetar begins to lose its power, the forces at work inside it are far from finished. This star's end is only the beginning of another, even more extraordinary event. As a magnetar's magnetic field decays and its core slowly cools, it enters its final stages. It can no longer support the internal pressures that once maintained its immense stability. The collapse is inevitable. The intense gravitational pull at its core becomes so great that it cannot hold itself together anymore. In its death throes, the magnetar either erupts in a supernova, a massive explosion, or it implodes, collapsing directly into a black hole. For most magnetars, the outcome is the creation of a black hole, a region in space where the gravitational forces are so intense that not even light can escape. The magnetar's once impressive size is crushed into a singularity, a point of infinite density, at the heart of the black hole. Surrounding it is the event horizon, the boundary that marks the point of no return. Anything that crosses it, whether matter or light, is consumed by the black hole, swallowed without a trace. But the process is anything but quiet. Before collapsing completely, the magnetar may release a massive burst of energy, a gamma ray burst, one of the most powerful explosions in the universe. These bursts are not just the remnants of the magnetar's magnetic death throes. They are signals sent across the cosmos, traveling at the speed of light, announcing the final moments of a stellar giant. As the magnetar's core collapses into a black hole, something incredible happens. the laws of physics as we know them are pushed to their limits. A black hole, formed from such a dense, magnetically charged object, warps space-time in ways we are only beginning to understand. The singularity at the center of the black hole represents a point where the known laws of physics break down, and our understanding of the universe itself reaches its boundaries. All that remains of the Magnetar is the black hole. Its energy, matter, and even its magnetic field are now contained within this cosmic prison. The magnetic field that once defined it vanishes, replaced by the black hole's own gravitational forces. However, new theories suggest that some of the Magnetar's unique magnetic energy may not entirely disappear. It might become intertwined with the black hole's rotational energy, potentially influencing its behavior for billions of years. Even though the Magnetar is gone, its legacy persists. Surrounding the black hole is a disk of gas and debris, the material that fell into the black hole during its formation. As this matter spirals inward, it heats up, emitting powerful X-rays that can be detected by astronomers across vast distances. This intense radiation can continue for millions of years, acting as a reminder of the star that once was. The death of a Magnetar is far from an isolated event. Its influence spreads throughout the surrounding space, creating ripples in the fabric of the universe. When a Magnetar dies in a supernova explosion, the resulting shockwaves can trigger the formation of new stars, enriching the interstellar medium with heavy elements. These elements, created during the star's lifetime and death, act as the building blocks for new generations of stars and planets. In a sense, the Magnetar's death gives birth to the next generation of celestial bodies. Even when a Magnetar collapses into a black hole, its death leaves a profound mark on the universe. The intense burst of gamma rays and other radiation released during the collapse can travel across vast distances, reaching distant galaxies and influencing the evolution of cosmic structures. These events may also trigger the formation of new black holes, or they could trigger a wave of star formation in nearby nebulae, pushing the life cycle of stars forward. So, what remains of a Magnetar once it becomes a black hole? The answer lies in the heart of the black hole, the singularity. This is a point of infinite density, where all the matter that once made up the Magnetar has been crushed together, creating a concentration of energy and gravity unlike anything else in the universe. There is no way for anything to escape once it crosses the event horizon. Any matter, any radiation, any signal from the past is lost forever. But as scientists continue to study black holes, new theories suggest that these enigmatic objects might hold onto something of their former selves. The Magnetar's extreme magnetic field, while seemingly gone, may leave a trace of its existence in the form of frame dragging, the twisting of space-time caused by the black hole's rotation. This phenomenon might cause the black hole to continue emitting energy in subtle ways, possibly influencing the space around it for billions of years. Even after a Magnetar's death, the energy it once released continues to echo across the universe. The gamma ray bursts, flashes of raw energy, that accompany its collapse are some of the most powerful and mysterious phenomena in space. These bursts radiate outwards, traveling at the speed of light, forever imprinted in the cosmic tapestry. Though the Magnetar itself has vanished, these bursts of energy remain as ghostly signals, traveling through the vast emptiness of space, carrying with them the story of the Magnetar's explosive end. But this energy doesn't dissipate into nothingness. Instead, it becomes part of the ever-expanding universe, influencing the formation of new stars and potentially even igniting new cosmic events. As matter falls into the black hole, the energy that was once part of the magnetar transforms, sometimes forming powerful jets that can blast outward at near-light speeds, carrying with them remnants of the star's incredible power.